Hi there and welcome to a new lecture on linear algebra. In today's lecture, after learning vectors, matrices, linear equations, different ways of solving linear equations, matrix multiplication, inverse, and determinants, today we are going to study subspace, null space, column space, row space, bases, and coordinate systems. In linear algebra, a linear subspace, or also called as, the one name is linear subspace. Another name is vector subspace, right? It's a kind of vector space that is a subset of some more larger vector space. A subset of some more larger vector space. In other words, a subspace is a vector space that is contained within another vector space. So every subspace is a vector space on its own, and there are some conditions. We call it as subspace if the zero vector belongs to V. It means zero vector should be included. Then, if we have vector u and vector v in this subspace, sum of u and v must be in V. Sum of any two vectors like u and v must be also there. And if u belongs to v, then multiplication of any scalar like c, the result that is cu must be in here as well. These are three conditions that we can take to see subspace. For example, here we have a subspace like x1 and x2, and there is a condition associated with x1. That means x1 must be 0 or positive. X1 must be greater or equal to 0. If I want to draw this one, so from x1, it starts from here, and from x2, we have no condition. So I can say that this part is my subspace. Now, I want to check. First, we check the first condition. It means the 0 vector must be included. So 0 and 0 is here, and it is included. So the first condition is okay. Then we check the second condition, that is sum of two vectors should be inside. For example, if I have A and B, and also I have C and D, right, then A plus C and B plus D must be inside there, right? For example, if I have like this one as, for example, -1 and 1, and also I have this one as 1 and 1, then 1 and 1 and 1 and -1, 2 and 0. So 2 and 0 is still there, right? It means, so sum is okay. So the second condition is also okay. Then the third condition is we should multiply with a scalar. Okay. So for example, if I have 1 and 1 and I multiply by -1, it will be -1, -1. -1, -1 is here. It is out of this space. So this condition is not okay. So this is not subspace, right? Because this one is out of this range. Let's see another example. We have a vector in R3, as you can see, W1, W2, W3 in R3. And the condition is 6 times W1 minus 5 times W2 plus 4 times W3 must be equal to 0. We need to check the conditions one by one. So as you can see here, the properties should say 0 must be here. It means when we say 0, it means the vector 0 is 0, 0, 0, right? And it will be 6 multiply 0 minus 5 multiply. That's okay. So the first condition, correct. Second one, if you have u and v in W, then u plus v must be in W as well. So if u is like this, u1, u2, u3 transpose, and v is v1, v2, v3, then u plus v1, u2 plus v2, this 3 should be there, right? Then 6, so we will put it here, 6 u1 v1 minus 5 v2 v2 plus 4 v3 v3 should be inside it, right? So then I say 6 u1 minus 5 u2 plus 4 u3 plus 6 v1 minus 5 based on this equation should be equal, right? And that's why you can see here, this one plus this one will be 0 based on the equation. So the second one is okay. Then the property number 3 say u in W, then cu should be in W. So we will put c here. 6 multiply cu1 minus 5cu2 plus 4cu3 is, we take its c out and we have already the 0 and it's okay. So we conclude that it is a subspace in R3. Subspace in R3. The null space, also known as kernel of a matrix. This null space refers to the set of all vectors when multiplied by a given matrix results in zero matrix. So for a matrix like A, if you have a null space of A, it's a solution of Ax equal to 0. For a matrix of A, the null space that we should like this null A is defined as V in Rn, where AV is equal to 0, or Ax is equal to 0. Null A is a subspace. If a linear function is one-to-one, it means we already have a definition of one-to-one function. The function maps distinct vectors from its domain to distinct vectors in codomain. In one-to-one function, there is a unique output or unique image for each input vector. When a linear function is one-to-one, the null space of the corresponding matrix contains only the value of zero vector. This is because the null space of a matrix represents the set of vectors that get mapped to the zero vector by the linear transformation defined by the matrix. So if a linear function is one-to-one, there are no non-zero vectors in the domain that map to the zero vector in the codomain, which means the null space only contains. So this condition happens. Let's see one example to better understand the null space. We have two vectors u and v, and also we have one matrix. This can consider as coefficient matrix. Now we want to check whether these u and v are in the null space of A or not. So what we do, based on the definition, we have to check whether Ax equals to B or not. We do a simple multiplication of matrices. A multiply U means matrix A multiply vector U. If you do simple multiplication, you will come up with these results. This is not equal to 0, so we can conclude that this U is not in the null space of A. But in the case of V vector, A multiply V equals 0, so we can conclude that AV is in null space of A. Let's see what is the difference between subspace and span. Based on the definition, we understood that a subspace is a subset of vector space with specific properties that we already examined all, making it a smaller vector space itself. Subspace contains its own basis and follows the rules of vector space operation. On the other hand, the span of a set of vectors is the collection of all vectors that can be created by a linear combination of those vectors. In previous lectures, we have this concept and we tried and examined different examples to understand the concept. So it's necessarily a subspace span, but it can be if the vectors in the set meet the subspace criteria. So in some cases, it cannot be a subspace, but in some circumstances that vector meet the criteria, it can work. So here we have, for example, this is a subspace V span V. So property number one, say 0 in V. It means we can say that, okay, if this is our S, then we say vector 0 is equal to 0W1 plus 0W2 plus up to 0WK, right? Which is in a span of S. And in the case of another property, we say that summation of two vectors included must be there as well. So we can say U equals A1 W1 plus A2 W2 plus AK WK, and V equal to B1 W1 plus B2 W2 plus up to BK WK, right? Then U plus V equals to A1 plus B1 W1 plus A2 plus B2 W2 plus AK plus BK WK, right? And this is still a span of S. Last one was this one, which says Cu equals to Ca1W1 plus Ca2W2 plus CAKWK be in a span of S. If these conditions happens, that we say a span is some kind of subspace. Column space and row space are important concepts associated with matrices. These column space and row space are used to represent two different aspects of the information that we have in a matrix. Column space is the set of all possible combination of a matrix columns. Or we can say a span of columns in A. On the other hand, row space is the set of all possible or a span of rows in a matrix. Both spaces, like column space and row space, are essential for understanding and solving the problems that we will have in future. The column space as call A, and call A is equal to AV in such a way that V is in Rn. Right? If a matrix A represents a function, then call A is the range of the function. And in here, we show by row A, and row A is always the transpose of column A. The range of a linear transformation is the set of all possible output vectors that the transformation can produce. And this range somehow can be equal to the column space of its standard matrix. This relationship of equality between column space and range highlights the connection between linear transformation and matrices, because the column space of the matrix captures the possible output of the linear transformation. So we already know that a linear transformation often simply referred as linear map or linear operator. So it's a kind of mathematical function that preserves vector addition and scalar multiplication. You remember already we had something like this. So a function that we have t v map to w is a linear transformation for all vectors like u and v in the vector space of v and all scalar in C. So we can say that tu plus v equal to tu plus tv, right? This is preservation of vector addition. Or on the other side, we can say that tcu equals to ctu, that is the preservation of scalar multiplication. So this is what we can have here. For example, this is we have t of x1, x2, and this maps to based on this condition. That is the relation between the variables. On the other side, we have a standard matrix. It's a kind of matrix that represents a linear transformation between vector spaces. In here, we have x1 to x4, as you can see, and we have a system of linear equations. So we can see we will bring the coefficient here 1, 2, 1, and minus 1. We can see that the standard matrix represents a linear transformation. So you can see here, this one here, this one here, this one here, this one here. We can conclude somehow that column space is equal to range. The column space of a matrix is what? Equal to the range of linear transformation associated with that matrix. The terms column space and range are often used interchangeably to refer to the set of all possible linear combination of the column of a matrix. Now, we want to check the relationship between matrix A and reduced row echelon form. We already learned about reduced row echelon form that was used to simplify and analyze system of linear equation and matrices. The transformation from the original of a matrix to its RREF primarily affects the organization and relationship of row while preserving the span of the rows. It is also changes the order of rows but maintains the relationship between the columns, although the span of the column may differ. And this kind of transformation simplifies the matrix and makes it easier to analyze and solve system of linear equation. So in comparison, the columns, the relationship between these two remain the same, and the span called R is not equal to called A. So column space of original matrix is not equal to column space of the RREF. In case of the rows, the relation between the rows will change, but the row space of A is equal to row space of RREF. Now we want to understand the concept of basis. If we have V, it is a non-zero subspace of Rn. So then a basis B for V, basis B for V, is a linearly independent generation of set V. This is the definition. A basis B for a vector space V can be defined as a set of vectors that these vectors are both linearly independent, this is one condition, and can be used to generate all vectors in V through unique linear combination. Bases are essential for understanding and working with vector spaces. There are two conditions. One is called as linear independence, and another is called as generation set. In the case of independence, the vectors in the basis B are linearly independent. It means that no vector B can be expressed as a linear combination of the other vectors in B. They are independent. In the simple words, we can say for any vectors like v1, v2 up to vn in B and a scalar like c1, c2 up to cn, the unique equation of c1, v1 plus c2, v2 plus cn, vn is equal to 0. This has only the trivial solution where all the coefficients are 0. So we can say C1, C2 up to Cn equal to 0. In the case of generation set, the basis is also a generation set for the vector space V. This means that every vector in V can be expressed as a unique linear combination of the vectors in V. It means for any vector V in weak V, there exists scalars like C1, C2 up to Cn in such a way that these V1 and V2 are vectors in V. For example, here you can see this is a basis in R2. And these are, any of them are some basis in R2. Here are some properties of basis. A basis is the smallest generation set. Smallest generation set. It means it's a basis for vector space in the smallest set of vectors that can generate or span the entire vector space. This means that we can express any vector, I emphasize any vector in the vector space, as a linear combination of the basis vectors. The second one, a basis is the largest independent vector in the subspace. A basis for the subspace is also the largest set of vectors within that subspace that is linearly independent. It means we cannot add any more vectors to the basis without making it linearly independent. And third one, any two bases for subspace contain the same number of vectors. This statement is also known as a replacement theorem. It means that any two bases refer to the same subspace have the same number of vectors. This number of vectors is called as dimension of the space. So dimension of V is the number of vectors in basis for a non-zero subspace. The number of vectors in a basis of a non-zero subspace V is called as dimension. We show it as time V. The dimension of a vector space or subspace is the number of vectors in basis for that space. Example, we want to find the basis of the V and its dimension if V is this subspace. Here is the condition, x1 minus x2 plus x3 minus x4 is equal to 0. So any vector like x1, x2, x3, x5 is in V. That satisfies the conditions, right? First of all, we say x1 minus x2 plus x3 is equal to 0. This is one condition, or equivalent this one. So let's try. We have x1, x2, x3 up to here, right? And this x1, x2, x3 can be written as minus x2. If we bring it in another side, we can write x1 equals to x2 minus x3 plus x4. So we bring this one into here, right? Instead of x1, we write this one. So this one can be x2 multiply 1, 1, 0, 0. 1, 1, 0, 0. And for x3, minus 1, 0, 1, 0. For x4, 1, 0, 0, 1, right? Then, based on this one, we can assume that, for example, u is equal to this one, u2, and u3, right? This computation shows that any vector x in V can be written as a linear combination of the vector u1, u2, u3. So the set of u1, u2, u3 is a spanning set of subspace V that we have defined here. We claim that u1, u2, u3, these are linearly independent sets. Considering that a1, u1 plus a2, u2 plus a3, u3 is equal to 0. So we show that this equation has only zero solution. It means a1 equal to a2 equal to a3 equal to 0. The equation can be written as this one. So comparing entries, we obtain that a1, a2 is equal to 0. But the equation defined here has only the zero solution. This one has only the zero solution. And the vector u1, u2, and u3 are independent. We can say that they are linearly independent. Therefore, we can say these are spanning set of V that we had here. That is basis of the V space. Since the basis consists of three vectors, then we say dimension is equal to 3. This is how we can solve this problem. A vector set B can be considered as a coordinate system of Rn if condition the vector set B span Rn, the vector set B is independent. Spanning and independence. We can say spanning and independence. The vector set B span Rn, which means every vector in Rn can be expressed as a linear combination of the vectors in B. For any vectors like, for example, V in Rn, there exists some coefficient like C1, C2 up to Ck such that V can be written as a linear combination of the vectors. For example, we can say B as C1B1 plus C2B2 plus CKBK, where B1, B2 up to BK are in B. This is one condition. Another one, the vector set B is linearly independent. It means there is no vector in B can be written as a linear combination of the other vectors in B without trivial solution. For example, C1, B1 plus C2, B2 plus CKBK is equal to 0, where C1 and C2 and C3 are some scalars, CK, and 0 represent the 0 vector, then these all are equal to 0. When a vector set B satisfies both these conditions, it can be considered as a coordinate system for Rn, because it forms a basis for Rn. A basis, I already defined, is a set of vectors that span the vector space and is linearly independent. Let vector B be u1, u2 up to uk independent. Any vector B in span B can uniquely represent as a linear combination. That means there are unique scalars like a1, a2, up k, such that A of this one, V is equal to a1 u1 plus a2 u2 plus a uk. So the proof is here. We have V, as in here, up to UK, and V, like for example any other one, B1 U, BU1, B2 U2, B up to BUK. So A1 minus B1 U, A2 minus B2 U2 up to AQ minus UK UK. So because B is independent here, then A1 minus B1 is equal to A2 minus B2 up to AK minus AK is equal to every vector in B is multiplied by, that is called as Cartesian. In Cartesian, one is considered as fixed and it will be multiplied by the others. So what do we have here? This is a B and this is a vector. Then we say 3 multiply this one, 6 multiply this one, and minus 2 multiply this one, which gives you 7. So it's 3 by 3, right, plus 6 minus 2 is equal to. Then, for this case, then again, this one multiply this one multiply that, and you give it this. So this was a lecture on subspace, null space, column space, row space, basis, and coordinate system. Please practice and feel free to ask me if you have any questions. Thank you for your attention and see you soon.